Hello everyone. In this video, I will be reviewing Calculus 2, and in particular, I will be reviewing some of the central concepts and ideas of Calculus 2 as they related to integrals and Riemann sums. In a couple of lessons, we will also be reviewing the techniques that were used to calculate integrals and Riemann sums. And this is to help to prepare us for what are called double integrals, triple integrals, line integrals, and surface integrals, all of which we will be studying throughout the remaining part of Calculus 4. So let's begin with a Riemann sum. A Riemann sum was a sum of the following form. For a function, which I'll generically call f of x, and for x's in the interval of inputs, let me generically say a to b, the corresponding Riemann sum was a sum of the following form. Sigma, that's the notation for sum, sigma add up terms of the form f of xi star times delta x. So looking at this expression, one could say, okay, there's so much notation here. What do each of these symbols mean? What is going on in this expression? So let's break down this notation piece by piece. So when you do a Riemann sum, the very first thing that you do is you take the interval of x values, a to b, and you split that interval up into smaller pieces or portions. So let's say we split the interval ab into a total of n smaller subintervals. So for example, if I drew off to the side a little xy plane, something that looks like this, and supposing that my relevant interval of x values is from here, a, to somewhere over here, b, then I could, for example, split up this interval of x values into 1, 2, 3, 4, 5 subintervals. Now, for each of these subintervals, I'm going to go in and I'm going to select a random x value. For example, a common choice is to go into each interval and choose the x value on the left side of the subinterval. Or it's common to go into each subinterval and choose the x value on the right side of each subinterval. Or you might choose the x value that's directly in the middle of each subinterval. That's common as well. Whatever you decide, we're going to let this notation xi star represent this x value that you have chosen out of subinterval I. So for example, in this drawing, if I chose the left-hand x value on each subinterval, then my x1 star would be a itself, x2 star would be this next value, x3 star would be here, x4 star, x5 star, and these would be the 5 x values that I would choose if I picked the left x value from each subinterval. By contrast, I could just as easily go into each subinterval and choose the x value on the right. So this one, this one, this one, this one, this one. That would be an alternative choice of the 5 values of xi star on each of the 5 subintervals. Or you could just as easily go in and choose the x value in the center, x1 star, x2 star, x3 star, x4 star, and x5 star. These would be examples of just x values that I've chosen out of these respective 5 subintervals. Now, when that xi star gets plugged into the function f, that is getting the corresponding output for each of these randomly chosen x values. In other words, if my graph of f of xy is doing something like this, then I would plug each of these chosen x values into the function to see the corresponding heights, on the graph. And those corresponding 5 heights would be the 5 values of f of xi star. Now, finally, if we look at what we called delta x, that notation delta x is standing for the width of each subinterval. Delta representing the change in x, delta x being the distance, the change between the x values at the left and the right side of the partition. So in this picture, for example, delta x would be the size of this gap right here. It would also be the size of this gap right here. It would also be the size of this gap right here, and so on. Delta x is the width of the different subintervals that you have created. Finally, the notation sigma is just telling us to add all of these terms together. Add the product f of xi star times delta x for every subinterval. So for example, in this drawing, my Riemann sum would be a sum of 5 terms because there would be one term, one of these products for every single subinterval that I've created in the picture. Now, from this picture, we can get a sense of how the Riemann sum is related to the graph of the function f of x. We have seen how each of the different pieces of the Riemann sum relates to the graph of f of x. But let's now see specifically what this sum of products is communicating to us about the graph. So I've gone back into this picture, and for the sake of an easy to read drawing, I'm just going to say that I chose my xi stars to be the x's on the left side of each subinterval. And say that they're right here in blue on the left side of each subinterval. So that my f of xi stars are located in these 5 positions along the graph of f of x. So here, for example, is the width delta x. And up here, this point has a height, which is given by the output of the function at x2 star, because this second dot is the x value that we have chosen out of the second subinterval, the one on the left. So f of x2 star is representing the height of this point, and delta x is representing the width of this particular subinterval. So if I take a product of those two quantities, like I have in my Riemann sum, the product of an output f of xi star with delta x is a product of the form height times width. the height coming from the output of the function, and the width coming from delta x, the width of each subinterval. And this is a very familiar formula to me from geometry. This product height times width in geometry is telling you exactly the area of a rectangle with these dimensions. The area of a rectangle that has a width of delta x, a width of delta x, and a height given by the output of the function at x2 star. So I'm going to draw that rectangle into the picture. The height of the rectangle given by this left endpoint of the second subinterval, and the width given by delta x, the width of that subinterval. So this particular product here is giving me the area of this particular rectangle. This is what it would look like for the second subinterval. But I could draw a similar picture for each of the other four subintervals, right? There would be another rectangle over here with a height of x1 star and a width of delta x. There would be another rectangle here with a height of x3 star, our third output. There would be another rectangle here with a height of x4 star, our fourth output. And then there would be another rectangle here with a height of x5 star, our fifth chosen output. The 5 terms in the Riemann sum are giving us the 5 areas of these 5 rectangles that have been attached to the graph of f of x. Now I put a little blank spot here next to the word area because what I have written so far is correct for functions that are entirely positive, like the one that I have drawn here. However, from time to time, you may be dealing with functions that are occasionally negative. For example, suppose that I draw the function f of x, and the function f of x does something like this on the interval ab. And suppose that I split it up into 1, 2, 3, 4 subintervals. And let's suppose that I decided, just in this situation, to take my xi stars to be the right endpoints instead of the left endpoints. If I plug each of those xi stars into the function, I get my f of xi star from the corresponding location on the graph. And so now I can see that some of the outputs of the function, some of the quote-unquote heights of the point, are negative because they are below the x-axis. Which means that if I look at the rectangle, which has a width given by delta x and a height given by the height of this particular output, if I look at this rectangle here, the quote-unquote area will be height times width, but this is going to be negative because the height of this point is negative. So for rectangles like these that exist below the x-axis, the Riemann sum is producing their area, but is producing a negative version of the area of that rectangle because the output of f of x I star is negative. Areas of rectangles are assigned negative if they are below the x-axis. So taking into account that some of the rectangles end up negative because they are below the x-axis, and some of the rectangles work out to be still positive because they are above the x-axis. The combination of these negatively signed rectangle areas and these positively signed rectangle areas, the sum of all of those quantities is what we call net area. Net area allows some rectangles to be positive in sign when we calculate their area, and some of the other rectangles to have negative areas if they are below the x-axis. And then when we add all of these signed areas together, there's going to be a little bit of cancellation between the positive areas and the negative areas. And the result of that cancellation is what's called the net area. So it's more accurate to say that the Riemann sum is the total net area of the rectangles under the graph. Now, let's notice something else also. Let's notice, in particular, in this picture, if I compare the net area of the 5 rectangles that I've drawn in red with the net area under the graph of f of x, those areas are pretty close in value. There are a couple of small differences. There are a couple of small gaps. For example, there are some pieces under the graph of f of x which are not included in the areas of the rectangles. And there are some pieces included in the areas of the rectangles which are not underneath the graph of f of x. But overall, those gaps are relatively small. And so the total area of the rectangles is a reasonably good approximation to the area under the graph of f of x. So overall, Riemann sums are exactly equal to the total net area of all of these rectangles that are attached to the graph of your function. And this in turn is a good approximation for the net area that is trapped between the graph of your function and the x-axis. Now, as we take our Riemann sum and as we allow the size of delta x to get smaller and smaller and smaller, this estimation becomes more and more perfect. And if you look here on Canvas for our page for lesson 12, which is the next lesson, as we are introducing double integrals for the first time, you can see some Riemann sum pictures for single integrals. And here in the upper left, for example, you see a right Riemann sum. And here we have a relatively large delta x because we only have 4 subintervals. And we can see that the gap, the discrepancy between the net area of the rectangles and the net area under the graph is pretty severe, right? Like we have this huge gap in this region We have this huge portion here where we're getting more area from the rectangle than we are under the graph. So in this situation with only 4 subintervals, there's a lot of inaccuracy. There's a lot of difference between the area under the graph and the area of these rectangles. But let's suppose that we cut the delta x in half so that instead of having 4 large subintervals, we have 8 smaller subintervals. We're still getting some pretty decently sized gaps, but we can see that shrinking delta x has caused a lot of the gaps to be filled in. And if we continue to shrink delta x, and if we continue to make our subintervals smaller and smaller, and make our rectangles more and more narrow, we can see that the size of the gaps between the rectangles and the graph of the function is getting smaller and smaller. And we can imagine that as we allow delta x to get extremely small, the gaps would be so small that we wouldn't even be able to see or notice them. Eventually, as delta x got very small, the net area of the rectangles would be pretty much an exact match for the net area between the function and the x-axis itself. That process of taking your Riemann sum and allowing the delta x to become smaller and smaller is what we call an integral. In a symbolic notation, we would say that the integral from a to b of a function f of x dx is equal to what you get if you take the Riemann sum of that function from a to b and you allow the width of your subintervals to get smaller and smaller and smaller, and you allow the width of your subintervals to approach 0. So all of this notation that I've just written down, if I were going to paraphrase this sentence, I would say that the integral is what the Riemann sum becomes when delta x gets extremely small. So in terms of the relationship between the integral and the Riemann sum, we could say two different things depending on what situation we're in. We could say that the integral is a perfected Riemann sum. You can take a Riemann sum and you can make delta x approach 0 to get an integral. Or you could also say that a Riemann sum is an estimate for an integral. A Riemann sum is an imperfect approximation for an integral. And this can be really useful if the integral, perfect as it is too difficult to actually calculate. If the integral is too hard to actually calculate, you can convert it back into a Riemann sum and calculate the Riemann sum instead. Now, we've already discussed a little about what integrals represent graphically. We saw that Riemann sums were an estimate of the net area between a function and the x-axis. And the definite integral, the integral is a perfected version of the Riemann sum. So the definite integral has its delta x so small that all the rectangles cling to the graph of f of x exactly, and so the definite integral is exactly equal to the net area between f of x and the x-axis. Those two are the same quantity. So just to give you a quick example of what it looks like to exploit this equation here, the fact that the definite integral and the net area are exactly equal to each other. Suppose I asked us, for example, to calculate the integral from -2 to 2 of the square root of 4 minus x squared dx. Now, depending on which instructor you had for Calculus 2, you might recall that there was some lunatic trig substitution that you, with lots and lots of work and careful calculation, you could calculate the answer to this problem. But it requires, like an entire page of work to find this integral using that method. Instead, let's use the fact that this definite integral is equal to the net area that is under the graph of the function I'm integrating for x values between the two limits of integration, -2 and 2. If I draw this function, either by hand or by using a graphing calculator, between -2 and 2, I find that I'm looking at a semicircle of radius 2. And so if I wanted to understand what the area underneath that circle was equal to, I can just use a geometry formula to answer that question. Just take the area formula for a circle of radius 2 and then cut that in half because I only have half a circle, and therefore I get that the value of the net area and therefore the value of the definite integral is positive 2 pi. Positive because this region is above the x-axis, so it would have a positive net area. Finally, let's just review a few physical applications, a few physical quantities that could be calculated using Riemann sums and integrals. So first of all, Riemann sums and therefore integrals can be used to estimate or to calculate distance traveled from speed. So for example, if I had a table showing me the speed of a certain object at different recorded times, say at time 0, it was going 20 miles per hour. At time 1, it was going 22 miles per hour. At time 2, it was going 24 miles per hour. At time 3, it was going, let's say, 23 miles per hour. And someone could say, for example, estimate the total distance traveled. I could say, okay, what I'm going to do is I'm going to pretend that the speed of the object was approximately constant on every 1 second subinterval of time. Of course, the object's speed is not constant, right? We can see that the object's speed is fluctuating. But if I assume that the object's speed is constant, that makes this a problem that is very, very easy to solve. And they only asked me for an estimate after all. So for example, I might decide to pretend that the object held a constant speed of 20 for this entire first second. And I might pretend that the object held a constant speed of 22 for this time interval between 1 and 2. And I might assume that it held a constant speed of 24 between this entire time interval 2 to 3. Now, with that assumption, if I asked myself, okay, how far did the object travel during this first second from 0 to 1, time 0 to time 1? I could use the DIRT equation, distance equals rate times time, which says that if your object is moving at a constant speed, you can find the distance traveled just by taking that speed of 20 and multiplying it by the amount of time that has passed. If I repeated that same process for the interval from 1 to 2, I would take the speed at that time interval and I would multiply it by the number of seconds that have passed. So from 1 to 2, 1 second has passed. And then similarly for the final period of time from 2 to 3, I'm assuming that the object speed was roughly fixed at around 24 units during that time period. So speed times time would be 24 times 1. 24 maybe meters per second held for 1 second of time. If I do that, then the total distance traveled would be 24 meters. Then if I wanted to know how far the object had traveled in this entire time interval, all the way from 0 to 3, all I would have to do is add up these three individual results here. So let's observe what we have just done, and let's just pick it apart. This 20 is the speed of the object that I have chosen to use from the first time interval. So I will say speed with T1 star plugged in. The speed with T1 star plugged in, the speed, the output that I'm choosing from the first subinterval. That here is 20. Here is the speed as a function of the second time that I've chosen out of the second subinterval. And here is speed with T3 star plugged in. The third speed that I've chosen to use, the speed out of the third subinterval. And on the right side, I have here the amount of time that's passed, the difference between the initial and final time, what we call delta t. So what have I just written down? I've just written down a sum of speeds chosen from the ith subinterval times delta t. And if I let delta t get very, very small, this sum would translate into an integral from whatever initial time to whatever final time of speed as a function of time dt. And the integral of speed, therefore, would give me the total distance traveled by an object. So this is one of the more famous applications of integrals to physical quantities. If you integrate an object's speed with respect to time, you get the object's distance traveled. Finally, let's review the process of calculating Riemann sums and getting information about integrals using things like tables and graphs. So for example, if you have a table of values for a function, let's say, 0, 2, 4, 6, 8, and a corresponding table of outputs for the function, -8, -6, -4, 0, and 15. If someone asks you for a left Riemann sum, a Riemann sum using the left endpoints, they're asking you to choose xi star and f of xi star to always be the left values on each subinterval. So those would be these four output values. The left one here, -8 from the first subinterval. The left one, -6 from the second subinterval. The left one, -4 from the third subinterval. And the left value, 0 from the final fourth subinterval. So the left Riemann sum would be the sum of those four outputs times the value of delta x, which in this case looks like would be 2 throughout. Calculate those products, add the results together, and this would be the left Riemann sum for this function based on this table. If instead someone asked you for the right Riemann sum, or for a Riemann sum using right endpoint values, in this situation, I would do exactly what I did before, except I would use the output values on the right end of each subinterval. So -6 from the right end of the first subinterval, -4, 0, and 15. Times the respective delta x's, and then added together. This would be the right Riemann sum for this function based on this table. So notice that the left Riemann sum and the right Riemann sum are pretty closely related. They share quite a number of terms in common. The only difference are these terms on the far ends. The left Riemann sum contains an extra term on the left side, and the right Riemann sum contains an extra term on the right side. For one other sort of non-standard method that's used to calculate or estimate definite integrals, we can also estimate definite integrals by setting up tables for the function that we're integrating and creating a Riemann sum for that function. So for example, suppose that I said the integral from 0 to 1 of the function, let's go ahead with the square root of 1 plus x cubed. I think you will find that this particular function is very, very hard to integrate normally using antiderivatives, even if you include applying weird tricks like trig substitution. So when you're in a situation like this, it's appropriate sometimes to estimate using a Riemann sum. For example, if you type this particular integral into a calculator like Symbolab or Wolfram Alpha, what they are doing behind the scenes is a Riemann sum estimate of some kind. So for example, if you wanted to get the calculation done quickly, you can choose a relatively large delta x value, like 0.1, which will split this interval into 10 subintervals. And then you can plug each of those x values into your function. In our case, the function we're integrating being the square root of 1 plus x cubed. You can plug each of those into the function to find the corresponding output values. And you might have a calculator there to help you. After that point, all you have to do is take that table and create either a left or a Riemann sum from that table. Exactly the same way that we did up in this example. So that concludes our review of the basic concepts of definite integrals and Riemann sums from Calculus 2.